All right. It's 2 o'clock, but my alarm didn't start. Anyway, welcome back, and please press the button which corresponds to your answer to this question. And I just want to remind you that today is a Monday. It feels like it's Tuesday. It looks like it's Tuesday, but it's not. It's a Monday. And you may want to reset the channel after changing the battery. Can I have my get back? Thank you. So everybody who has a lab section on Monday has it today. Wednesday people, Thursday people go according to the regular schedule. Tuesday people, what do they do? Today, nothing. Are you a Tuesday person?
Should I go on later this week?
No. What does the email say? Tuesday next week. So the next Tuesday is an actual Tuesday, and well, exclusively for people who have a lab on Tuesday, it's going to be next week on Tuesday, according to the regular Tuesday schedule. All right? Yes. Bless you. Is the wrong answer? No. Is the right answer? This is a very common case when you have to compare two situations. Normally, one we call the initial, another we call final. Something should happen. So the initial situation is when the object travels keeping velocity constant, and we are applying a force. Do we know the force? Well, strictly speaking, yes, we do, because we have it found last time before we left the room. By the way, 109, the number of students on the roster officially on the student link. 44, the number of pictures I have received. 5, the number of students who calculated the kinetic frictional force. The question was about static, but basically all calculations have been correct. So here we know that if the force of gravity is equal to what number? 50 newtons. And the normal force, which should compensate it, have the same magnitude, 50 newtons, and it is sliding. The frictional force should be equal to the coefficient of not static friction. If it's not static, it's kinetic. We only have two options to choose from: kinetic friction times normal force, which gives us 20 newtons And because the velocity is constant, the applied force must have exactly the same magnitude. That's where we finished last time. Nothing new so far. But now we make a change. So the situation changes, and we have to compare the new situation with the old situation. What does change? The applied force, 20 plus, well, 20 times 2 equals 40. We double it. Numbers don't matter. It could have been any set of numbers. What matters is it was traveling with constant velocity if we double the applied force. If we make any kind of change, the first question to ask is, how does that change affect all other parameters? What other parameters? Well, mass. If we double the applied force, do we change the mass? If we double the applied force, do we change the force of gravity? If we double the applied force, do we change the normal force? If we double the applied force, do we change the force of kinetic friction? There is no reason to friction be different. If this is the same, if this is the same, if this is the same, the friction stays the same. But the applied force now is stronger. So, constant velocity, what does it tell us about acceleration? What number? 0. Net force now is not 0. It doesn't even matter what is equal to. We can calculate. If we're using the numbers, the applied force is 40. The force of friction is still 20. The net force equals 20. 40 minus 20, 20. But what's important is it's not 0 anymore, which means the acceleration is not 0 anymore. That's what changes. It was 0, the velocity was constant. It's not 0, the velocity just cannot be constant anymore. Just can't. Just impossible. It's speeding up, it moves faster and faster. So it's a completely different case. Any questions? Well, what should happen if we start applying a force? This is what we've been doing. Well, of course, it stops moving, but does it stop moving immediately? No, it should take some time. How much time? Well, it depends. But the third question, of course, is related to the third situation, the new diagram. Still gravity, still normal, still friction. But if we don't apply any force, there is no applied force. So the net force is not 0, but the net force now points to the left, it slows it down, and eventually it stops. But not immediately. It takes some time. It always takes some time. Like in this problem. There's a little guy on a sled. Maybe it was sliding down the ramp first, but then it eventually stops. What's the reason to stop? Well, friction. It has initial speed 4 meters per second, and the final speed equals 0, because stop means 0. So that's exactly the same situation we just have discussed. What do we do? Well, of course, we applying the Newton's law, but in addition, we also have to apply our previous knowledge about how acceleration, distance, time might be related. So this is an example of how we put together, knit together, puzzle together pieces of information related to this specific situation. So what is the set of important variables we have to think about? Mass, gravity, acceleration, displacement, time, initial velocity, final velocity, frictional force, coefficient of friction. What kind of a friction? We only have two options to choose from. This is a coefficient of what kind of a friction? Kinetic. It's sliding, so kinetic friction. Where else? Basically, that's probably it. Now, these variables, these parameters, acceleration, time, velocity, displacement, they are connected via specific set of equations. How many equations can you write? Velocity equation, motion equation, the third equation which has no name. But if we talk about forces, well, we can add an abstract net force, normal force. So if we talk about forces, they related to each other by other set of relationship. You see, so far, the blue lines and the red lines, well, black lines, sorry, the blue and black do not connect. They are disconnected. It means it's unsolvable. It must be some kind of a connection. All variables must be connected. Only then it could be solvable. Every connection, like this, of course, represents a specific equation, either a definition or a law. So there is one important connection which is still missing between at least two variables. So what do you think? What is the missing connection between what and what? And which force? No. Acceleration and the mass, and there is a special name for that special force. Acceleration, mass, and net force. Not frictional, not normal, not gravity, net force. These three variables are related by a different equation, Newton's second law. That's it. Problem solved. Problem is solved. No physics left. We just have to write those equations, those connections. So, for example, here, distance traveled, delta x, which is equal to the displacement, same direction, no point of the return, supposed to be equal to initial velocity times time plus acceleration times time squared divided by 2. Velocity equation. Final velocity should be equal to the initial velocity times, well, nothing, plus acceleration times time. The third equation, which has no name, final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. In this case, displacement and distance, same things. All right. So one set of connections is right in front of our eyes. Another set of connections related to forces. We must draw a free body diagram. We can use this picture. For example, actually we already have it even better. But if we want to use this free body diagram, we should choose, well, strictly speaking, two directions, x and y. So normal force and force of gravity cancel each other out. So they have the same magnitude. F normal is equal to mg. And the acceleration times mass should be equal to what? Well, strictly speaking, that should be equal to this plus, oops, it has to be horizontal. So I have to be very careful. Plus this, that's what the net force is equal to. These two forces cancel each other. So the acceleration is equal to this over m. Well, that's an arrow. It has a magnitude. It has a component. If we want to calculate the component, and that's what we're doing, we have to write what symbol? What sign? Negative sign, a minus, because this component has to be negative relative to our choice of positive x direction. And why do I choose my positive x direction to the right? Force of habit. I could have chosen it differently, but in that case, my initial velocity would have negative component. Yeah. So we just have to pay attention to all arrows. So what do we have here? It has to be equal to -1 times the magnitude of that force. That has to be the force of kinetic friction, which is supposed to be equal to the coefficient of kinetic friction times the normal force divided by m. In turn, that should be equal to well, minus, because the component should be negative, 0.05. That's the coefficient of kinetic friction. Times, as we said, the normal force should be equal to the mass times g, and we divide it by mass, so we actually don't even need to know the mass in this particular problem. It's getting canceled, but still. So it's m over m times 10. So it turns out the acceleration equals -0.5 meters per second square. I want to point out again at a very, very common situation. We solve a problem, we write variables, a lot of letters are involved. We have to keep in mind the exact meaning of each letter we're using. For example, where was it? Here. What does this m mean? What does this m mean? That's it. Don't be confused. Always keep in mind the exact meaning of each letter. You will be all set. So what do we do next? How long would it take? Well, to calculate the time, we can use the velocity equation. Final velocity is 0, initial velocity is 4. It's clearer here, 4. The acceleration is -0.5, done. 4 divided by 0.5. (40/5). Anyone? That's it, 8 seconds. Any questions? This? Oh, you're right. Well, first of all, that's not a DS. I'm sorry. That's why when I write, I know I have, and I told you so, I have a bad handwriting. I can't do anything about that. So that's why I always read what I write. I know I have bad pronunciation, but, well, it's better than nothing. So it's -1 times the coefficient of friction, which is 0.05. Still looks like a DS, I don't know. Sure. Times, that's the normal force. The normal force equals mass times 10. 10 is G. So that's what's I'm trying to fit in it. Oh. All right. What did happen to mass? Mass getting canceled, m over m. So I can finish this calculation, -0.5, not an S, a 5. Meters per second squared, which is what I brought over here, the acceleration. The magnitude of this acceleration is equal to 0.5 meters per second squared, but it points to the left, opposite to positive x direction. That is why component of the acceleration is negative. The object is slowing down. Well, a force is a measure of an interaction between two objects. An object number 1 and object number 2, a force. This is the single exception. We don't really treat this force as one force. There is an interaction here between the surface and this box, or wherever it is. What we do is we break it down into two components, and we treat those components independently as individual forces. One component of the contact force is the real force, but the component of that force which is parallel to the surface, that's what we call friction. Another component of the same actual physical force, which is perpendicular to the surface, that's what we call normal force. Strictly speaking, between you and me, if we draw a free body diagram, we should draw only contact force. That's the actual force. But we don't do that. We always resolve it into the components. The parallel we call friction, the perpendicular we call normal, and we count them as individual forces. For example, here. First, ignoring friction. As soon as there is some kind of an angle, the normal force is not equal to the force of gravity anymore. So this is what this question is about. Well, first of all, do we know this angle? It's a 3, 4, 5 triangle. So clearly, that's supposed to be 30, 60, 90 triangle. Yes? No? Please. You either agree with this statement or disagree. There are no other options. Yes, this is a 30, 60, 90 triangle. Press 1. No, this is not a 30, 60, 90 triangle. Well, press anything else. Doesn't really matter. So it's 1 or no 1. All right. 86, good enough. Nice. So first, I would like to suggest to everyone to check your answers to the math self-test. There is a very similar question, and it's a working moment. We need to know, yes or no, what kind of a triangle is that? The right answer is no. That's not 30, 60, 90 triangle. And of course, the fastest way to check it is just actually calculating this angle. Oops. 3, 4, 5. The tangent of this angle is supposed to be equal to 3 over 4 or 0.75. So the angle itself is supposed to be equal to the inverse tangent of 0.75, which is, yes, you moved 37 degrees, and so no. But it is a known angle, 37. So what do we do? Well, there is, of course, another force acting on it, force of gravity. So in general, when we solve any problem, we have only two opposite situations. The situation number one, all forces are parallel or perpendicular to each other. Situation number two, at least one force is neither parallel nor perpendicular. Gravity is not perpendicular to normal. Normal is not parallel to gravity. So what do we do? In a case like that, we always replace the bad force, the force which messes it up, with its components. Force of gravity has two components. Has one component for the force of the force of gravity is parallel to the surface, and second component of the force of gravity is perpendicular to the surface. We could have used the normal force, but trust me, it's faster and easier to break down the force of gravity into the components. So what we're doing now is we're solving a different problem, which is absolutely equivalent to the original problem. Instead of solving the problem like that, normal gravity, we solve a problem like this. Ramp, normal, mg parallel, mg perpendicular. These are standard names: parallel component, perpendicular component. Well, normally parallel to the surface, perpendicular to the surface, because if it slides, the velocity, the acceleration also parallel to the surface. So we have many, many directions, many, many vectors which are parallel to the surface. So if we wanted to, we could have used x and y axis, but the most convenient choice for the axis is like this. One axis is parallel to the surface, and another is perpendicular. Well, if we look at this picture, we can immediately make two conclusions. Number one, m times a should be equal to now I'm going to point at the vector, at an arrow, and you should move either yes, you agree, or no, you disagree. M times a is equal to this. No. Is equal to this. What's left? M times a is equal to that. That's it. That's how it works. We know, well, let's write it down. Mg parallel. And we know that the force of the normal force Fn should cancel that component of the force of gravity which we call perpendicular to the surface. So in terms of the magnitudes, the normal force must be equal to this component of the force of gravity. If only we knew those components. Well, what can I say? It's up to you. There's no physics left. Right? The rest is math, right? Angle triangles. Well, let's do it very quickly, just to make sure we are on the same page. This is the angle of the incline. So the vertical line always is perpendicular to the horizontal line. If we want to, we can use this angle, which is supposed to be equal to 90 minus this one. So for example, if this is 37, that would be 90 minus 37. 46, 56, 53, 53. It's a long day. It's a long life. So now this arrow, this arrow represents the force of gravity, and these two arrows represent components. So this angle is 53, the same angle as here, between the same directions. This is 90. Components are perpendicular to each other. This is 37, or what we call theta. This is what we call mg parallel, and this is what we call mg perpendicular. So according to our knowledge of how right triangle works, it has to be equal to mg times cosine of theta, or mg times sine of 90 minus theta. It's up to you which angle you want to use. And here for the parallel, that has to be equal to mg, which is the hypotenuse, right, of this triangle, times the sine of theta or if you prefer, mg times cosine of 90 minus theta, again, whichever you prefer. That's it. We're done. So for example, if we want to calculate the acceleration, we just have to use the expression for this component, sine theta. And if there is no friction, the solution very simple. Mass cancels. Acceleration should be equal to g times the sine of this angle. For the normal force, we should use the second relationship. It should be equal to m times g times cosine of theta. Well, in this it's cosine of theta. And here, well, it's wherever it is. We know the mass of this block is 2 kilograms. G equals about 10. Cosine of 37 degrees. That's our normal force. Any questions? Now, of course, the next step is what do we do? I'm going to go to this first. What do we do if there is some friction? We just have to add one more arrow to the free body diagram. So remember, we have two different situations, two different regimes. Situation number one, nothing is moving, which means static friction is acting on it. Situation number two is sliding. Could have been sliding with constant velocity or speeding up. Still, in that case, we should use kinetic friction. But the free body diagram is the same for all cases. Now we just have to add one more arrow. So everything, what we've said about components stays. This is mg parallel, and this is mg perpendicular, and this is theta. So the expression for the normal force doesn't change. It's still going to be equal to mg perpendicular relative to the surface, still going to be mg cosine theta. But now we have to use this expression for calculating, well, this specific problem tells us we have to calculate the force of kinetic friction. So the force of kinetic friction should be equal to the coefficient times normal force. What about acceleration? Well, now there are two reasons, two sources for the acceleration. First of all, as it was before, the m times a should be equal to this. It stays, doesn't disappear. Still, the component of the force of gravity, which is parallel to the surface, acting down the ramp. But now, since friction is not zero anymore, we should, well, again, strictly speaking, we should add a negative component. So plus -1 times the magnitude of the frictional force. Frictional. Or, in our mind, we could have chosen x and y axis like this. So velocity points down. Acceleration also points down because object, well, in this situation, acceleration actually is zero. Yeah? So, even easier. But if friction would have been not so strong, it could have been speeding up. That wouldn't change our equations. Still, we would use exactly the same equations. Now, I want to go to this problem. What's wrong with this? Oh, wrong is a strong word, yeah. But this force kind of messes it up, because this force, again, neither parallel nor perpendicular to kind of natural directions, vertical and horizontal. So what do? Exactly same thing we did to the gravity just a minute ago. Whenever we have a force which has a certain angle relative to some natural directions, we replace that force using its components. So this arrow, which is 20 newtons long, and all right, so let me see. This angle should be equal to this angle, and 180 minus 120, this angle should be equal to 60. This angle should be equal to 60. So it points down below the horizontal by 60 degrees. That's it, geometry. So this arrow has two components. This is what we usually would have called the component which is, well, horizontal or parallel. Again, because that's the direction of the motion. So we can call it parallel or horizontal. And there's another component which we can call perpendicular or vertical. And for each component, we can use our knowledge of how right angle triangle works to calculate the magnitude. So for the parallel component, the magnitude will be equal to the force itself, 20 newtons, times cosine of 60 degrees. And for the vertical component of the applied force, that should be equal to the magnitude of the applied force times the sine of 60 degrees, or cosine of 30 degrees. Sine of 60, cosine of 30. So now the problem has more forces, but they are easier to deal with. So now what we have is an object. We have force of gravity acting on it 50 times 10 equals 500 newtons. There is no friction, ignore friction. There is normal force acting up. And instead of this actual applied force, we can use two components. This, which is equal to 20 times cosine of 60, and then this, which is equal to 20 times the sine of 60. Done. So what we have to do now is just help ourselves to choose pluses and minuses. And we can write the Newton's law relative to each axis. Relative to the vertical axis, everything is balanced out. So one force pointing up, the normal force, must cancel out two forces pointing down, F normal minus mg minus 20 times sine of 60 equals 0. Zero. Which immediately answers the question about the normal force. Now, for the acceleration we use x components, everything which is parallel to the acceleration. So what we have is 20 times cosine of 60 has to be equal to m, which is 50, times a, which is acceleration we were looking for. Done. Solved. Any questions? All right, moving on. How much time does it take? Or distance traveled? So every problem like that has two different problems in it. This situation from a physical point of view is no different from this situation. On one hand, it is about forces. On another hand, it is about motion with constant acceleration. So the strategy is exactly the same. We should use a combination of, well, two different but related topics. One related to the motion with constant acceleration, and second one, which is related to forces. So here, time. The acceleration, m times a, will be equal to m times g times cosine of this angle minus the coefficient of kinetic friction times m times g, sine of this angle times cosine of this angle. coefficient times normal force. And this is my angle, theta. So if I calculate the acceleration using this expression, actually, you see m, again, getting canceled. We don't really need to use the mass for this particular situation. What do we do to calculate the time? Well, we know the distance traveled, 5 meters. It's a 3, 4, 5 meter ramp. So we start from rest. The initial velocity is 0. What else do we know? Well, distance traveled supposed to be equal to the initial velocity times time plus a half of the acceleration times time squared. So the acceleration comes from the Newton's second law. That's 0. Distance equals to 5 meters. We solve it for time if we want to. Where else can we solve? Oh, Atwood's machine. This is another example of a situation when objects make a coupled motion. Atwood's machine, one of the first devices which been used hundreds of years ago, actually, to measure accurately g, the acceleration due to gravity. So 100 grams, 100 grams. Of course, the system is in equilibrium. It doesn't matter which is higher, which is lower, doesn't matter. The tension here is equal to mg here, the tension here is equal to mg here, same m, nothing is different. I have to break the equilibrium. I can add some mass, and this is a 10-gram weight. And in that situation, it doesn't matter which is higher, which is lower. The one which is heavier starts moving down. The one which is lighter, starts moving up. That's it. That the motion is coupled. What do we know about it? Well, first of all, if this travels 1 centimeter up, this travels exactly 1 centimeter down because the string doesn't stretch, which means they travel same distance, they have the same speed, and the acceleration for both have the same magnitude. Plus, we know that if we don't clamp, don't hold on the string tension, well, getting redirected, it changes its direction, but the magnitude inside the rope, magnitude of the tension, stays the same. That's it. So all we have to do is just write two equations. The first equation for the first object, the second equation for the second object. Let's choose positive y direction upward. We have mg down, tension up, and the acceleration for this object points down. We have little m times g down, tension up, and the acceleration for this object points up. These are different accelerations, but they have the same magnitude. So little m times a should be equal to tension minus little mg. And here, relative to this choice of the positive y direction, everything which points down should have a negative component. And I'm using this variable a for the magnitude of the acceleration. So strictly speaking, the component, the y component of this acceleration is equal to this. So big M times negative a should be equal to, well, tension is directed up, and gravity is directed down. This is the second equation. The fastest way to solve it is to multiply the second equation by -1. So I just want to change the sign in front of every term. Negative becomes positive, positive becomes negative. And now I can take these two equations and I can add them up all together. So big M plus little m times acceleration will be equal to, you see, this is a t, and we are adding a negative t. What's happening? Cancel. So done. And what we have here is plus a big M minus a little m times g. It's not the only way to do it algebraically, but the fastest way. So we can solve this equation for the acceleration. The acceleration will be equal to this mass difference divided by the total mass times g. But in real-life experiment, which has been done, we could have measured the acceleration. Yeah? It travels down. We can time it. We can measure distance traveled. It starts from rest. And if we know the acceleration, we can use this expression to calculate the free fall acceleration, to calculate g. That's how it's been done originally. What time is it? Oh, OK. I don't know what's happened. Doesn't ring anymore. So thank you very much. We are almost done with mechanics, simple mechanics.
Since today is Monday's schedule, I have Tuesday lab, actually, but since today's not the schedule, but they're not meeting Tuesday lab.
You were late.
What? Sorry?
Today. You were late for the lecture, right?
Actually, I came on.
So probably.
Or no, I think I came exactly at 2, so maybe I didn't listen to what you said.
All right. Anyway, if your regular lab time is a Tuesday,
Yep.
go home. Your lab will be next week on Tuesday.
Next Tuesday. Okay.
Next Tuesday.
Okay, thank you.
Yes.
I told you about a final conflict with nutrition.
Yes.
And I talked to the nutrition teacher, and she doesn't believe me that I have this final at the same time, and she refuses to move it. And I've told her, I've shown her the picture of the schedule, and she just doesn't believe me. I don't know why. So is there going to be a way?
What do you mean? She doesn't believe you.
Because it's a Monday class, 3 to 6, so it's a weird. I guess they didn't time it right. It was the 2 to 3 Monday, Wednesday, Friday, and she thinks that we're having it on a day that the university didn't approve, so she refuses to move it, thinking it's just an accommodation. And that you moved your time to a different time.
Well, there's a table.
Yeah, I know.
There's a chart.
I've showed it to her. She doesn't I don't know what to do.
So you have a class.
Yeah.
That's a
right
class.
After this, from 3 to 6, that has the same exact time, the same exact day for the final.
All right, can you send me an email again?
Yeah, I'll email you.
Yes, thank you. Can you also please?
Sorry?
Can you also just give me some information more about that class?
Yeah, I will. Also, was there a sign-in sheet today?
Yes, it was.
There was?
It was. So it should be somewhere around here. Yes.
Yes, and I was wondering because I had to walk home. It's too late.
Here. Well, you're gonna have to go back to your clicker tomorrow. Okay. Hi, Bruno.
Hello.
I'm sorry. I'm gonna be out in a minute.
Oh, that's all right. We have time.
It's actually 3.
You're still plugged in.
Hello, everybody. So, I hope you got my email message saying there were no labs this week, right? Yay! Trying to get everyone back in